Hello students, welcome to the world of chemistry. This is Dr. Vikram Panchal and I am dealing with chemistry spectroscopy, UV visible spectra, and in this lecture number 26, I am discussing in this lecture selection rules for electronic transitions. In earlier lecture, I have explained you the first selection rule for electronic transition, and that was spin quantum number rule, that delta S should be 0 when electronic transition occur and if it is allowed electronic transition. Okay, now we will discuss here about the second rule, that is center of symmetry rule. Okay, in lecture number 18, I have already explained you about molecular orbitals. That how molecular orbitals form by merge of atomic orbitals. Okay, so there are various types of molecular orbitals like sigma BMO, sigma ABMO, sigma star ABMO, then pi BMO, pi star ABMO, n orbitals, etc. I have explained you all these things. So according to molecular orbital theory, molecular orbitals in which center of symmetry present known as G orbital or Girard orbital. Girard means equal, similar. So it is G orbital. And molecular orbitals in which center of symmetry absent known as U un-Girard orbitals, means they are not similar, unequal orbitals. Okay, so according to MO theory, sigma BMO, pi star ABMO are G orbitals in which center of symmetry present, and sigma star ABMO, pi BMO are un-Girard orbitals, U orbitals, where center of symmetry is absent. Okay, so when electronic transition occur, like G to U orbitals and U to G orbital, then they are symmetrically allowed transitions. As for example, sigma to sigma star transition is symmetrically allowed. Pi to pi star transitions are also symmetrically allowed transitions. So these are allowed transitions. Okay, and both have higher values of epsilon. Now, when electronic transition occur like G to G and U to U, then they are symmetrically forbidden transitions and difficult to occur, as for example sigma to pi star transitions and pi to sigma star transitions. These are forbidden transitions and practically very difficult because they have very low value of energy. Okay, so this was about the center of symmetry rule for electronic transition. Now we will see second rule for electronic transition. Third rule for electronic transition, and that is plane of symmetry. When electronic transition occur in molecular orbitals which have same plane, that is in plane transition. Then it is known as allowed transitions or easy transition, which has very higher value of probability, that is epsilon. As for example, sigma to sigma star transition with certain amount of energy, or pi to pi star transitions are allowed transitions according to plane of symmetry. Why? Because both transitions are in plane transitions. That means the plane will remain the same. The plane of symmetry will not change during this transition. So these are allowed transitions. When electronic transition occur in molecular orbital which are in different plane, that is known as out of plane transition. Then plane of symmetry. Then it is known as forbidden transition. And it has very low probability. For example, N to sigma star transition as well as N to pi star transitions. Why? Because the N orbitals and pi star or sigma star orbitals are in different plane, and therefore these transitions are not allowed, or we can say forbidden transitions. They are possible. These transitions are possible. But probability will be very low. Very, very less. That is the condition of this type of transitions. Now we will take one example so we can understand this type of transitions. Let us take carbonyl compound, carbonyl group, C double bond O group. You know, in carbonyl group there is double bond between carbon and oxygen, and oxygen has lone pair of electrons which will be in n orbitals. Okay, one bond is sigma, another is pi. So let us see how molecular orbitals of carbon and oxygens are formed. I am not interested in discussing sigma to sigma star transition in this case. That is why I have kept sigma bond like that. Okay, now how pi bonds form, let us see this one. These are pi BMO orbitals of carbonyl group, like banana, and these orbitals have 2 electrons. So this is pi BMO and this is also pi BMO. There are 2 electron clouds of pi BMO. Along with this, they must be having pi star orbitals, and they are lying in this direction, but they have the same plane of pi orbital. So pi star orbital have total 4 lobes, half lobes. So these are pi star ABMO orbitals. Pi star ABMO orbitals. Now where is n orbital then? Well, this is one plane of pi BMO and pi star ABMO, but n orbital would be in a different plane. So one n orbital we can show like this and another can be in this direction. But these two orbitals are having different plane of symmetry. So this will be n orbital having lone pair of electron, but the plane of symmetry will be different. So both will be in a different plane of symmetry. So these are n orbitals. Okay. Now, when in carbonyl group, we have sigma, sigma star, pi, and pi star orbitals in the same plane. But n orbitals in different plane. So in carbonyl group, sigma to sigma star transition and pi to pi star transitions would be in plane transitions and smooth. So they are known as, their probability will be maximum. So we call them, so they are allowed transitions. Okay. So normally pi to pi star transition occur is very smooth with absorption of radiations having range of 200 to 800 nanometer. Okay, and which will give K bands. Now what is K band? I will explain you in next lecture.